What is up, everyone? Welcome to another episode of the Rockstar Scientist Cohort videos. Today, we're going to be talking a little bit about chemical bonding, a little bit about atoms, and we're going to kind of put it together with some of the other parts of the course so that you can see why is chemical bonding important in the first place. Like, how does it really relate to what we're studying here as a part of biology? Because, as you know, chemical bonding, that's very much chemistry. So we want to talk about how does chemistry relate to biology as far as our bodies and how they work. Also, we want to connect how that relates to other parts of the course like water. And maybe we'll touch on the plasma membrane to show how all of this chemistry is related. The idea is so you can see the connections between the material, and rather than feeling like you're just memorizing a bunch of different facts, you can actually see how they're all related to create a network within your brain so that you can see how different things influence each other, which will enhance your ability to remember these individual parts of the course. So, without further ado, let's get into it. All right. Before we can talk about chemical bonding, we need to talk a little bit about the atoms that make up the different chemicals within our body. Sorry about that little glitch there. The computer froze up for a second. Okay, so let's start with the individual atom. So all mass on Earth, everything that you can actually touch, is made of matter. Even the air around us, it's all made of matter. There are two different things on Earth. There's matter and there's energy. And we talk about this later on when we talk about ecosystems. Because matter, the physical parts of our world, are constantly recycled. So they cycle through an ecosystem or through an environment. What does that mean? Well, think about the food that you eat. The food that you eat either comes from other animals or it comes from plants. And even the food that comes from animals, the reason that they are food to us is because they ate plants, or they ate something else that ate plants. So ultimately, we eat things that eat plants, or we eat plants ourselves. That's the physical, tangible things that we eat. We digest that, we use that to make energy, and then we defecate. We release that back into the environment. There are bacteria and fungi within the soil that break down our feces into particles that then feed the plants so that the cycle starts all over again. Or if we or another animal dies, we decay and we then release nutrients into the soil, which plants use to start the cycle of life all over again. So if you remember the show The Lion King, the movie The Lion King, it's very pertinent because we're talking about the circle of life, how we ingest things, we grow, we release them back into the environment so that other things can grow and continue to feed the earth. Energy is a little different. So energy is not matter. And we're talking about matter today. So energy is something else. Plants take energy from the sun and they turn it into food. We then eat the food. The physical part we excrete, as I was just saying, but the energy we use to move our bodies around. So the energy that I get when I eat, a cupcake, for instance, because that's really high in glucose. The energy that I use when I eat a cupcake, I use to move my body around. Some of it. I guess some of it also turns into fat because, cupcakes, they're really great, but they're totally high in sugar, and our bodies turn sugar into fat. The part of that I do use, I use to move my body around. And as you guys know, if you move your body around a lot, you get really sweaty. You get sweaty because you get hot. So when we utilize energy, we use it to move, and the excess is released as heat. So that goes back out into the world around us. So matter is constantly recycled. It becomes a part of us, we defecate or we die, it goes back into the soil, it becomes part of animals again in a circle forever. So matter cycles through the environment. Energy, on the other hand, like that from the sun, comes in and then it goes out. So energy moves through an ecosystem, matter moves within it. And again, we're talking about matter today. All matter is made of these things that we call atoms. And I'm going to go ahead and pull up a picture of the periodic table here. You guys get to see a little behind the scenes of how these Adobe rooms work. Oops, no, not that. Let's look at the periodic table. So the periodic table is the bane of many introductory chemistry students' existence. Many first, second year students have a hard time with the periodic table, but you guys are lucky. You don't have to really know any of it. I just want to point out some very basic points. This is a list of all of the elements that exist on Earth. Each one of these elements represents a single individual atom. So here we have an atom of hydrogen, which is the most simple form of matter that exists in the universe. Here we have helium. Here we have carbon, which is really important because this is what makes up sugar. We also have sodium, which you guys know mixes with chlorine to make sodium chloride, which is table salt. Down here is gold. Here's lead, things that you're probably familiar with. Here's aluminum. These 118 elements are what make up the entire universe. And they all represent individual atoms. So the reason that we have what we call matter is because these individual atoms act like Lego pieces. And they hook up together to make what we see in front of us. So like, I have a Swell water bottle here. It has a lot of aluminum in it, among other atoms. So those atoms combine together to make this actual object. Let's see what else. Same thing with this porcelain coffee cup. There are several atoms, and I should know this, but I don't remember what makes up porcelain or whatever this is, clay. But different atoms on the periodic table will combine in a specific combination to make this specific product or this specific compound that makes the world around us. So each one of these are different Lego pieces, and if you combine them together in different ways, you get different materials that we experience in our everyday lives. So what's the significance here? Well, first off, let's talk about the structure of an individual atom. Atoms only have 3 parts to them, which makes them very easy to understand. The first part is the proton. The second part is the neutron. And the third part is the electron. So I'm going to draw the proton with the red, the neutron with gray, and the electron with yellow. So we're not going to talk much about protons and electrons. We're primarily going to focus on, we're not going to talk much about protons and neutrons. We're going to focus primarily on electrons. But really quick, when we look at the periodic table, you'll notice that each one of these atoms has a number. Every element on the periodic table has an individual number that uniquely identifies it. That number tells us how many protons an atom has. So hydrogen here has 1 proton. That's why it's the most simple form of matter, because it's 1. If you have less than 1, you have 0, which means it doesn't exist. There's no matter there. If we look here, again, at gold, gold has a number of 79. So that means it has 79 protons. If we look at lead here, which you know is very different than gold, you'll see that its number is 82. So quite literally, the main difference between gold and lead is 3 protons. And that's really it. That's the main difference. But you guys don't need to know that for this exam. I just wanted to let you know what protons do. Protons are located in the center of our atom. And we call the center the nucleus. You may recognize this term if you have already worked with the cells portion. A nucleus is something that we also have in our cells, and that's because nucleus is just a fancy word for center. So our cells have a nucleus as well, because the person that first looked at them through a microscope was like, that kind of looks like the center. I'm going to call it the nucleus. Another thing that atoms have, this is an atom just in case we forgot, in the nucleus are these things called neutrons. And neutrons, as far as this class goes, you don't need to know a lot about. They're there to help stabilize the protons. They just make sure that everything stays nice and safe in the center. Because if a proton escapes, that changes the identity of the atom, and we don't want that to happen. We don't want carbon, which is what we are mostly made of, to lose atoms and turn into something like hydrogen, because then we would evaporate, and that's not good. So the neutrons help give stability to the atom. And atoms are very stable, so you don't need to worry about them collapsing or anything like that. So then lastly, we have these things called electrons. And electrons exist outside of the nucleus in these regions that we call orbitals. Orbitals. We also call them electron shells. But the idea is the electrons orbit the atom the same way that the planets orbit the sun. And we see that they also can orbit in different layers. And this is important because this means that the atom itself, because it has these different electron shells, have different layers that go outward. So an atom is a lot like an onion or an ogre, depending on how you want to look at it, if you catch the reference. Because onions have layers. And like an onion, our atom, the centermost layer is going to be the smallest. And as you get out, they get larger. Also like an onion, you have to finish building the inner layer before you can start to build outer layers, or else the whole thing collapses. So the orbitals of these atoms can hold different electrons. And you don't really need to know this for the exam. I just want you guys to be able to understand this so it's not just memorizing facts. You actually have something in your brain to pull from if you get asked a question on the exam. So as you can see, this innermost layer is the smallest. It can only hold 2 electrons. Again, not important for the exam. I just want you to understand how this works. This next layer is a bit larger, and it can hold 8 electrons. Now this is important. This number right here is what we call the magic number. 8 is the magic number. And the reason that it's magic is because we talked about how protons dictate what identity an atom has. The neutrons help give the atom stability. The electrons are going to be what determines what atom another atom will bond with. So the electrons are what get to decide these relationships between atoms that create the world around us. And that's the important part of this module, is we want to understand how do atoms combine together to make the things that make up the cells in our skin, or the cells in our hair, or the atoms in the material objects around us. So we're going to be focusing primarily on the electrons today because that's where it all stems from. And it all has to do with this magic number of 8. Because atoms really want to have 8 electrons in their outermost shell. So right here you see this specific atom has 1, 2 atoms in the first shell, and 1, 2, 3, 4, 5, 6 in its second shell. This atom wants to have a total of 8 electrons in its outermost shell. Before we get into that, there is a term that we use to describe what these electrons in the outermost shell are called. Because they're so important, because these outer electrons are going to determine what atoms another atom will bond with, they have a very specific name. So here is the first term that you guys need for this part of the module. And that is valence electrons. So valence, you may notice, looks like another term you might be familiar with, and that is valence. So those of you who have a grandma probably know what a valence is. If not, a valence is a curtain that occurs on the outermost side of your curtain assembly. So you have your real curtains, and then you have your valence curtains that are kind of hang up above, and they're basically just for decoration. Ultimately, they're just an outer layer to your curtain setup. Valence can also be pronounced as valence. And here, valence electrons are any electron in that outer shell. So here, this atom, because it has 6 electrons in its outer shell, has 6 valence electrons. 6 valence electrons. But as I said, all atoms are looking for this magic number. So all atoms want 8 valence electrons. So what this atom is going to want to do is it's going to want to team up with another atom so that they can share, or so it can steal electrons so it can have that full outer shell. And that's what we're going to be talking about for the next few minutes, is how atoms will either share together so that they can achieve that number of 8, or how they can steal from other atoms so that they can get that number 8. But before we go there, there's one more thing that we need to talk about. Atoms, each one of their pieces has a specific charge to it. And if you guys know anything about charges, you can either be positively charged or negatively charged. Like if you see a battery, it has a positive end and a negative end on it. And that's what we're talking about here. So protons have a positive charge. And really quick, that's not to say that atoms are batteries, because they're not technically a battery. It's just that that's the way we explain batteries, is they have a positive and negative end. Atoms are the same way. They have a positive end and a negative end. The positive end is the proton, and the negative end is the electron. So if you look at this, protons, P is for positive. Neutrons are neutral. So they aren't positive or negative. But electrons, they have the negative charge. And this is important to know because atoms in their normal state are what we call neutral. That means they have the same amount of positive as they do negative. So this atom right here has 6 protons. It has 6 positive charges, 1, 2, 3, 4, 5, 6. Because it has 6 protons, it must also have 6 total electrons. 1, 2, 3, 4, 5, 6. Oops, I drew too many protons. Sorry about that. So we're going to get rid of these 2 in here. Okay, so total electrons, we've got 2 in this first layer. 1, 2, and then we have 4 in the second layer. 3, 4, 5, 6. So we have 6 total electrons, which have a negative charge. And we do that to show that if we have 6 positive and 6 negative, they cancel each other out, so we have 0. Okay, so now looking at this, after I've redrew it, how many valence electrons does this have? It doesn't have 6, because it has 2 in the first layer, and then it has 1, 2, 3, 4 in the second layer. 2 plus 4 equals 6. So it only has 4 valence electrons. So this atom is going to want to find a partner that also has 4 valence electrons so they can hook up and have that total of 8. Okay, so let's talk about how atoms will look for partners to have this total number of 8 electrons in their outer shell. And if you didn't catch this positive or negative, that's fine, because we're going to talk in detail about it here in a second. So let's talk about a real example. There's this atom called boron. And boron has 2 electrons in its first shell. And it has 1, 2, 3 in its second shell. So this atom has a total of 3 valence electrons. So if it wants 8, how many is it looking for? Duh, it's looking for 5. So it just so happens there's another atom called nitrogen. And nitrogen has 2 atoms in its first shell, so that one's full. That's what these lines mean. And it has 1, 2, 3, 4, 5 in its second shell. So as you can see, this is a pretty good match for boron. Boron and nitrogen, they really like each other because 3 plus 5 equals 8. And again, this is the magic number. So let's look at what happens. Under normal circumstances, boron's electrons are orbiting around it by itself. Just, again, like the planets orbit the Earth. Same thing with nitrogen. All of his electrons are orbiting him. But when these two come together, when they get close to each other, they're going to be like, oh my gosh, you are perfect. It's like, yeah, I think so too. You're my soulmate. So they're going to come together because they complete each other. So when they come together, what they're going to do is they're going to start sharing these electrons. So now they both have 8 electrons in their outer shell because they're sharing 5 and 3. This is called a covalent bond. And let's talk about why this is called a covalent bond, because like a lot of other science terms, there's a clue to what this word means in the name. So the word co here literally means to share. Like if you cooperate with somebody, cooperate, you are sharing the responsibility of some project. If you if you are part of a co-op. A co-op is where you share the responsibility of managing a business. So co means to share, and valent here just means valence electrons. So this word literally translates to share valence electrons. And that's what these guys are doing. Electrons. They're sharing valence electrons so that they can both have that magic number 8. So now they are stable. They are perfect. They feel complete. The way that we draw this is with a solid line. So if we were to draw this, we would show B with a solid line is connected to N. This solid line means there's a covalent bond. It means they're sharing electrons. And I wanted to say this because this may show up on the exam. They may show you a picture of this and say, what does this mean? I'm pretty sure it's an exam question. What it means is they're covalently bonded together, which may be one of the answers. Or another answer may be that they're sharing electrons. It's important to remember that. Okay, so really quick, there are 3 types of chemical bonds we talk about in this module. The first is covalent, which we just covered. The second is going to be ionic. And then the third is going to be hydrogen. Now we're going to talk about these in order from strongest to weakest. Because covalent, as we just talked about, when they find each other, they're soulmates, so they're going to grab on real tight. What we're going to see as we go down the list, they get a little bit weaker each time. And again, why are chemical bonds important? It's because if we just have one element, one single atom by itself, we can call this, like boron we just talked about, we call an atom or / an element. Same thing if we have nitrogen all by itself. That's a single atom, can also be called an element because they mean the same thing. Now when we combine them together with this covalent bond, they now become what we call a molecule. Or we can also call those a chemical. Anytime you have more than one atom combined together, it's no longer called an atom or an element. It's called a molecule or a chemical. So even a chemical that you don't think is a chemical, water, which is H2O. Water is still technically a chemical because it's more than one atom combined together. And again, you can also call it a molecule, doesn't really matter. Same difference for all intents and purposes. Okay, so we talked about covalent bonds, which are the strongest. Let's talk about ionic bonds now. And let's talk about an ionic bond that you are all familiar with. And that's the ionic bond between sodium and chlorine to make what we call sodium chloride. Another name for that is table salt. So sodium and chlorine bind together in a little different way than we were talking about with like boron and nitrogen. Their relationship is a bit more complicated because they don't really like to share, and we'll talk about why here. So sodium has 2 electrons in their first layer, so that one's full. Their second layer, sodium has 8 electrons, so that one's full, which means it only has 1 lonely electron in this last layer. Chlorine has a full first layer, full second layer because he's got 8 there, and in this outer layer he has 7. So again, we've got a good match here because 1 plus 7 equals 8. But there's a difference here. Chlorine looks at sodium and is like, you know what? Man, you are what I've been looking for, but I have 7 valence electrons, you only have 1. I don't really want to share with you because it's not really fair. I bring a lot more to the table than you do. So instead of sharing, chlorine's going to be like, yoink, give me that. And he's going to steal the electron from sodium. So sodium is out this extra electron. But as it turns out, sodium is kind of fine with that because it had that 1 lonely electron in that outer shell. Well, now that that's gone, what does it have underneath? It has a shell with 8 electrons in it. So now it's like, dude, that's cool. I've been trying to get rid of that thing for a minute. Take it, get it out of here, I'm good. And chlorine's like, well, thanks. I really appreciate that because now I have 8 electrons in my outer shell. So everybody's nice and stable. Everybody's nice and happy. But something has fundamentally changed about these atoms. Because remember, I told you protons and neutrons are equal so that we have neutrality. So sodium used to have 11 protons, and it used to have 11 electrons. And when you do the math, 11 positive and 11 negative equals 0. So originally, this had a net charge of 0. But chlorine just came in and stole an electron. So instead of having 11 and 11, it has 11 protons and only 10 electrons. So if we do the math here, 11 positive and 10 negative, so 11 minus 10 gives us positive 1, because 11 minus 10 equals 1. So sodium now has what we call a charge. It has a positive charge because 11 minus 10 is positive 1. So we can write this as it has a positive charge, or we can say it is electropositive. They both mean the exact same thing. And you may see this on the exam. It may say positive, or it may say electropositive. It may say neutral, it may say electroneutral. It may say negative, it may say electronegative. They mean the exact same thing. Positive and electropositive are two ways of saying the exact same thing. And the exam's going to try and use those terms to trick you because it wants to see if you know what they mean. So keep that in your back pocket. Positive and electropositive are the same thing. This used to be neutral. Electroneutral means the same thing. So now let's look at chlorine on the other side here. So chlorine used to be neutral as well. It had 17 positive protons, and it had 17 electrons that are negative. Which again, you do the math. Positive 17 and negative 17, they balance each other out, they equal 0. But chlorine just stole an electron from sodium. Oops, let's draw this black. So now instead of having 17 electrons, he has 18. And if you have 17 positive minus 18, you get negative 1, which makes sense. He just took a negative charge, one negative charge, so his balance is now going to be negative 1. So chlorine now has a negative charge, also known as electronegative. And this is why these two are going to like each other and stick together. So what do you know about positive and negative charges? Well, opposites attract. So this positive charge is going to attract this negative charge. They are going to be like little magnets. Just like the north end of a magnet and the south end of a magnet are going to stick together because opposites attract, these two are going to stick together like little magnets. And that's what's going to create this ionic bond. Okay, so why is it called an ionic bond? Again, there's a clue in the name. The word ion literally means to be positive or negative. So an ionic bond means the positive and the negative are going to stick together like little magnets because they're attracted to each other. So this is different than the covalent bond. The covalent bond, remember, they're sharing electrons, so they are gripped tight together. They're like holding hands. They never want to let go. This is more like a magnet. And as you know, magnets, you can stick them together, pull them apart, stick them together, pull them apart. That's why this isn't as strong, because it's not that they're grabbing on for dear life. It's just that they're attracted to each other, so they're going to stick. So that's why this is not as strong. It's because magnets can easily pull apart and stick together. The covalent bond, it's like they're welded tight. And you know, if you want to break a weld, you got to break it. Magnets, not so much. So that's the ionic bond. So now let's talk about the, come on, go where I want you. It's not gonna. Let's talk about the hydrogen bond. There we go. There we go. So hydrogen bonds are the last one, and these are the weakest. And that's because they're not really much of a bond at all. Hydrogen bonds are more of an attraction. So let's look at our buddy water here, because water is really important in all of our material. And water, again, is H2, so 2 hydrogen and 1 oxygen, H2O. So now, do you remember what this line right here means between the oxygen and the hydrogen? That is that covalent bond. So that means that this oxygen and these 2 hydrogen are sharing a total of 8 electrons. Now, the three of them together are sharing 8 electrons. But if you look here, oxygen is massive compared to hydrogen. Oxygen is like 16 times larger than hydrogen. So just using your brain, if you have like a full-grown adult, which is huge, and 2 little children, and they're all sharing the weight, they're all carrying the weight of electrons, who's going to be holding on to the most? Well, clearly the adult, because they're going to be able to carry more stuff. The same thing is true here. If these 3 are sharing 8 electrons, oxygen is so big, he's going to be holding on to most of those electrons. So let's say he's holding on to like 6 electrons. So then hydrogen is, each one is maybe holding on to 1 electron. So oxygen is holding on to most of these electrons at any given point in time. So that means that because oxygen is holding on to so many electrons, we say that oxygen has a partial negative charge. So that can be written as partially negative, or the other way we learned how to say it is partially electronegative. So oxygen in water we say is partially negative, also known as partially electronegative. Now this is not a full-blown negative like chlorine where it stole an extra electron. This is just a tiny, tiny, tiny bit negative. Which means that, if you remember our battery example, if you have part of it that's negative in this molecule, then the other part must be positive. So that means the hydrogen, which is not holding on to many electrons at all, we call it partially positive. So again, partially positive slash electropositive. So now you see we have a duality. This is a lot like a magnet. A magnet has a north pole and a south pole. The water molecule also has a type of north pole and south pole. It has this partially negative end and this partially positive end. Because of that, we say that water is a polar molecule because it has this north pole and the south pole. Or you could think of it as, it can't make up its mind. It's a little polar because it's a little bit of both. And this is going to be important. We'll talk about this here in a second. But before we get there, what do you think happens if we put another water molecule next to this one? So we have this hydrogen that's partially positive, and we have this other oxygen which is partially negative. Well, you probably already guessed it. These two are going to be attracted to each other. This hydrogen is going to want to attract this oxygen because they have a very slightly positive and negative charge. So again, this isn't a full-blown positive and negative like sodium and chlorine. They're not going to stick like magnets. It's going to be very loose attraction. In fact, you could think of it that hydrogen is just a little sticky. So think of this more as like sticky tack, like the blue stuff you used to use to hang posters on your wall. You get them up, and a week later they'd fall down. Same basic principle. It's an attractive force. It's not super strong. It's actually pretty weak. But this is a hydrogen bond. It describes this attraction of hydrogen to other polar molecules, or in this case, oxygen, which is a part of the polar molecule that is slightly negative. So hydrogen bonding is not an actual bond like we were talking about. It's more of an attraction. And it's not like a magnet bond like sodium and chlorine. Again, it's just a very loose attraction where they're going to be compelled towards each other. This is important because this is what gives water its cohesiveness. So you may remember, water is cohesive. I know you've heard of an adhesive before. And adhesive is something that sticks to something else. Like you have glue, it sticks different things to each other. Cohesive means it sticks to itself. So if you take a drop of water and put it on the table, you're going to see that it beads up in a little ball. If you do that with something like gasoline, it will not do that. If you take a drop of gasoline and put it on the table, it's going to spread out. It's because gasoline is oil-based, and oil is not polar. Water is polar. And this is important because this talks about something else that we need to know about, which is this idea of things being hydrophobic or hydrophilic. Come on. There we go. So we have these two terms, hydrophobic and hydrophilic. So hydrophobic, as you guys know, means afraid of water, whereas hydrophilic means it likes water. So hydrophilic things are what we call polar, because water is polar, so it likes other polar things. Hydrophobic, on the other hand, these are non-polar. So they only like other non-polar things. This is why water and oil don't mix. This is why gasoline doesn't beat up the way that water does, because gasoline, oil-based products are non-polar. They're going to spread out. Water, though, it's polar, so it has that cohesive property. This is also why, like, vinegar and water mix. Vinegar is going to be a polar molecule, just like water. You can mix them together. But oil and vinegar and oil and water, they won't mix, because you're trying to mix a polar and a non-polar molecule. So hydrophobic molecules are going to be non-polar, whereas hydrophilic are going to be polar. And this has a lot to do with the plasma membrane. So as you know, the plasma membrane is made up of a phospholipid, or a phospholipid bilayer. Phospholipids have a phosphorus on the end, which is polar, and then this fatty tail on the other end, fatty acid tail, fatty acid tail, which is nonpolar. So this gives them their dichotomous polarity, nonpolarity, which means half of it is hydrophilic and the other half is hydrophobic. And the crazy thing about these is, because they have this duality, if you put them in moisture, if you put them in water, they will do something very specific. So if you take a handful of these phospholipids and dump them into water, they're going to take on a very specific organization. It's not drawn to scale. This is just to show you what I mean. So if you take a handful of phospholipids and drop them in water, they're going to organize in this fashion, where they're going to make this bilayer all by themselves. Finish drawing this here. We've got all our tails and our phospholipids pointing towards each other. You guys get the idea. So if you take these and drop them into water, they're going to automatically organize this way, because the hydrophobic tails are going to want to tuck in so they can be safe from the water. Whereas the hydrophilic heads are going to be facing the aqueous side. So as you probably know with cells, on the outside, we have our blood. So on one side of our cells, we have our blood, which is mostly water. So it's very, very hydrophilic. On the inside, we have the cytoplasm, which is also mostly water. So it's very hydrophilic. This is very useful for our cells because all they have to do is make these phospholipids and they're automatically going to organize in this fashion. They don't really need to expend a lot of energy to build this because the hydrophobic and hydrophilic aspects are going to want to organize this way automatically. So then what we have here is this inside, the layer, or the middle of this bilayer is going to be hydrophobic. So they're going to stick together. And what this does is this allows our membrane to be very selective because it has both a hydrophilic side, which likes water, and a hydrophobic side, which doesn't. So not only does it organize this way automatically, but it also allows the cell to be very specific on what it lets in and what it lets out, which is where we talk about diffusion versus facilitated diffusion versus active transport, which we'll save for another video because this is already a lot of information. I want you to take this and digest it before we go into anything else. Okay, so we're going to go ahead and stop there. As per usual, if you have any questions, feel free to reach out to me directly. There's my email, my phone number, or feel free to reach out to the Life Sciences inbox. And if you want some one-on-one time, you can always book it with me or your course instructor or anybody on the team. We are all more than happy to help you. Well, cool. Thanks for sticking with me through the video. I will see you all next time. And again, if you have any questions, just let us know.